Hi, everybody. You should be able to see my screen now.
Yep,
Okay.
we see it. Yep.
Okay. So, okay. So today I want to talk about this beautiful work that I did with Wouter Kastrik and Verkoutere, who are both in Leuven. And so what we did, we were breaking the decisional Diffie Hellman problem for class group actions. And so to be able to tell you about the work that we did, I first need to start with the Diffie Hellman. And so the Diffie Hellman exchange is, or at least in this textbook version, is about Alice and Bob. And Alice and Bob wish to share some secrets over an insecure channel. And the way they do it, or the way they can do it, is that they agree on a prime number p, which is, we agree on prime number 1009, and they choose some number, 515. Well, if you look at the powers of 515 modulo the prime p, there are altogether 252 different powers. And so if you look at the communication of Alice and Bob, then they're communicating over insecure channel. So they agree on the prime, some number, and there are some 252 different powers of that number. What Alice and Bob can do, they choose some of the powers. So Alice chooses 113th power, Bob chooses 89th power. They both compute the appropriate powers of the number 515, and they send it to each other over the insecure channel. Well, and of course they receive the corresponding values of the other person, and then what they can do, they take the numbers that they received, take their own power, and magically they get the same answer, 663. So now, after doing this back and forth, Alice and Bob now share the value 663. So this is the very basic way. Slight way how to generalize it using group action, using groups, is that Alice and Bob can also agree on a group and an element in the group. And the element generates some subgroup of size n. So we had the group, which was the multiplicative group of non-zero residues modulo 1009. The element was 515, and the group size was 252. And then, so they agreed on the group, on G and on N. Alice chooses some multiple, Bob chooses some multiple. Alice computes, well, the multiple of the generator, G to A. This is multiplicative notation. She sends it to Bob. Bob sends his G to B to Alice. And then, of course, Alice can compute the appropriate multiple of the answer that she received from Bob. And Bob can do the same. And in the end, they both obtain G to the power A times B. So this is the basic Diffie Hellman exchange. So now Alice and Bob, they're sharing the value G to A times B. And the question is how secure, well, how is this an actual secret? And so if you look at the slide again, Alice chooses some A, Bob chooses some B. And so the idea is that nobody but Alice, Bob should be able to should be able to know A and B. So in particular, the important assumption is that if the adversary who's seeing everything that's on the insecure channel, so she knows G and G to A, she should not be able to compute A from this information. But this is actually not enough because the shared value is G to power AB. And so what we actually want is the computational Diffie Hellman assumption is that if the adversary sees the whole conversation, so she knows G, the generator, and Alice's and Bob's elements, she should not be able to compute the value G to AB. So this is the actual assumption that we're making. But if you think about it, then even though G to AB shouldn't, the adversary shouldn't be able to compute G to AB, it can still be easy to predict at least some part of it. And ideally, we would like the shared value to be a shared secret. So it should be ideally indistinguishable from a random element or a string. And so that's the decisional Diffie Hellman problem. So if you're given a tuple, well, you either know, well, if you're giving a tuple that comes from this Diffie Hellman exchange, can you determine whether the guess G to C is actually the correct G to AB? So more precisely, if with probability 1/2, the exponent C was random, and with probability 1/2, the exponent was the correct one, C was A times B, can you tell just by looking at G to the power C? And so the decisional Diffie-Hellman assumption is that no computational bounded adversary can do this. No computational bounded adversary can guess correctly whether the element G to C that he sees was actually G to AB or not, better than just guessing randomly. Okay. And so now we have this Diffie-Hellman exchange, and the question is, we have all these assumptions, how secure is this exchange actually? And the disappointing news is that if you take a group that is used in cryptography nowadays, so then it's susceptible to an attack using a quantum computer. So there's this Shor's algorithm that allows you to compute A from knowing G and G to A in a polynomial time using a quantum computer. And then, of course, it's very easy to solve the decisional Diffie-Hellman problem or the computational Diffie-Hellman problem. So we do the following workaround. We, instead of using groups, we will represent the groups by sets. So trying to get rid of some of the structure that could be exploited by Shor's algorithm. And so the example of a group action that we want to keep in mind is the affine space. So an affine space has some underlying vector space, and the vector space has an action on the affine space by setting a point, and a vector gets sent to, well, the point translated by the vector. And this is an action, so it doesn't matter if we translate it by two vectors or if we first add the two vectors together and then translate the point. It is a free action, so if we translate the point by two vectors and we arrive at the same point, then the vectors must have been the same. And it is a transitive action. So whenever I have 2 points in my affine space, there is a vector that sends one of the points to the other. So affine spaces are a beautiful example of a free and transitive action. And at the same time, if you look at the affine space, it's just a set of points. So it hides the structure of the vector space. There is a bijection between an affine space and its underlying vector space, just choosing an origin A. So once again, if we go to affine spaces, then we took these vector spaces with so much structure and got rid of the structure. So now we only have points. So this is why we are excited about group actions. And now, if we do have a group action, how do we do the same Diffie-Hellman exchange just from the group action? Because if we get rid of some of the structure in the group, then it might be more difficult to apply all these attacks. So we have a group G, and we assume that it's commutative, and we have some set X, and we suppose that G acts on X by free intransitive group action. So we will denote it by the star. Well, we can choose a point in X, so basically choosing the origin in the affine space. And then Alice can choose a random element in the group, and she can act by the element on the chosen point. Bob can do the same. Now they can swap their values, so they send the resulting points, and each of them can then act with their element on whatever the other had. So Alice receives B star Y from Bob, and then she acts with A on it. But because this is a group action, it has to be the same as acting by A times B. Bob can do the same thing. He receives A star Y from Alice, and he acts by his element B on it. Because it's an action, he needs to receive the same answer, B times A, which is A times B star Y by commutativity. And we can actually set the same Diffie Hellman setting in this mindset. If n is the order of G, and we can assume that n is prime, then it is actually the group Z mod n Z star acting on the set, which is just the powers of G. If we take a number, it acts on the element G by taking the corresponding power. And so the group action that is actually used in isogenin-based crypto is by these class groups in imaginary quadratic fields. And so let me skip the definition of the class group, but it is a very algebraic and very beautiful and classical object. So we just have this very well-studied group that was already known to Gauss and is very, very well understood. And we let it act on the set of elliptic curves. So this is a very crazy sounding thing, because elliptic curves are just some equations with y squared is equal to x cubed plus ax squared plus bx, where a and b are some numbers in a finite field. And I claim that there is an action by this class group, this very classical number theoretic object, on the set of elliptic curves, and that this action is free and transitive. Well, it's kind of hard to write down how this action looks like, but just the easiest and basically the only thing that I can easily write down is this ideal. You have to trust me that this is a right thing to act by. Takes this equation, y squared is x cubed plus ax squared plus bx, and it sends it to another equation like this. So it's something that just from the coefficients of this equation sends it to a coefficient to an equation with different coefficients. And so this is the basic setup in isogenin-based crypto, group actions. And there is a similar decisional Diffie Hellman problem. So if we have, this is the direct translation of the problem, if we have a tuple of elliptic curves, and we know that, well, these curves, A star B, B star E, C star E, are just the results of the action of A on this origin E, we're asked to figure out whether, well, the same thing, A times B is equal to C, where these are now ideals.
So, Jana, sorry to interrupt, but you're running a little short on time, so maybe it's good to keep that in mind.
Yeah, thank you. Yeah. So what we do is that we use these characters that are known for the class group and are kind of easy to compute on the class group, and we show how to compute it directly from elliptic curves without knowing anything about the ideals. So this allows us to, using these characters, allows us to break this decisional Diffie Hellman problem. And so let me just tell you when this attack works. The short answer is that it works in polynomial time in almost all cases. So it works for density 1 set of cases. And so I will stop there.